For today's pre-lecture video, we're going to concentrate on Archimedes' Principle, or why things float. According to popular legend, when Archimedes was resting in a bathtub, he actually had a thought that occurred to him that would explain why things float. It caused him to yell, "Eureka!" and maybe run through the streets of Rome naked. Who knows? So let's think about some things that we know related to why objects float in Archimedes' Principle. We know that when something is immersed in water, it seems to weigh less than when it is in air. If you yourself are in water, you know that you seem to feel a little lighter. You know that if you try to lift something while it's in the water, it's much easier than it is when it's in air. It obviously weighs less. You might not know that if an object is less dense than the fluid that it's placed in, it will float. This is actually true. This can help explain why a large luxury ocean liner can float in the water when it's absolutely huge. It just has to be less dense than water. Most people can float in water, unless they're particularly dense. And a helium-filled balloon we know floats in air. This is also governed by Archimedes' Principle and is simply due to the fact that helium is less dense than air. So, what is Archimedes' Principle? Archimedes' Principle says, when a body is completely or partially immersed in a fluid, the fluid exerts an upward force on the body equal to the weight of the fluid displaced by the body. More simply stated, the buoyant force on an object is equal to the weight of the displaced fluid. So let's review how we find the weight of something when we're dealing with fluid. When we're dealing with fluid, we often talk about the density of the fluid, which is its mass over its volume. The reason that we do this is because with a fluid, it's much more likely that we know what the volume of fluid is. And so if we think about the weight, which is equal to mg, when we're trying to find the weight for a fluid, we can rearrange this and mg can be replaced by rho, and the volume of the fluid times g. So this is the way that we often find the weight of something, like the weight of a fluid, because we know the volume. And this is really just equivalent to mg. This is something that we need to remember. We're going to use it a lot when we're dealing with Archimedes' Principle. So, how can we use this? Okay, it says that the buoyant force is equal to the weight of the displaced fluid. So the weight of the displaced fluid this is going to be equal to the density of the fluid times the volume that is displaced times g. If we remember this makes it really easy to use Archimedes' Principle. We always can then say that the buoyant force is equal to the density of the fluid, this is the fluid that the object is in, times the volume that's displaced. This basically is how much of the object that is floating is under the water. That will tell you how much fluid has been displaced. And then finally, times g. Let's look at some examples. How about for a person? A person who weighs 550 newtons empties her lungs as completely as possible, and then it's completely immersed in water, which has a density of 1,000 kilograms per cubic meter. Her apparent weight is now 21.2 newtons. What is her density? All right, well, let's try to look at this. So, first of all, I think I want to know what the mass of this person is. If her weight is 550 newtons, I know this is equal to mg. So I'm going to find her mass. And if I do, I find the mass of this person is 56.12 kilograms. I'm going to keep that in mind for later. If I want to find her density, the reason I was interested in is because the density of the person is going to be the mass of the person over the volume of the person. And so I already have one piece of that information. I need to figure out what the volume is. All right, so let's think about this. So let's imagine here's a big container of water. Here's the person. We imagine that the person is on some sort of scale so that we can weigh her. So there's the tension. The tension is going to represent the apparent weight. The person has a certain weight, which is mg, but also has a buoyant force acting on the person. And that's what causes her weight to appear to be smaller. If I look at this in terms of the sum of the forces, which are equal to 0 because she's in equilibrium, because she's just completely immersed and she's in a static equilibrium, I have tension plus the buoyant force minus mg is equal to 0. All right, let's go to the next page to think about that. So what I had was tension plus the buoyant force minus mg was equal to 0. All right, so I know the tension and the weight. I'm going to rearrange to find the buoyant force is going to be mg minus the tension. The tension, remember, that is the apparent weight, if you don't remember that. That's what she appears to weigh. It's reflected in the tension of the scale that the person is hanging from while being underwater. So the true weight was 550 newtons. The apparent weight was 21.2 newtons. The difference between these represents the buoyant force, which turns out to be 528 newtons. Now, that buoyant force, the buoyant force is equal to the weight of the displaced fluid. Which is equal to the density of the fluid times the volume that's displaced times g. Well, now we'll be able to figure out the volume that's displaced is equal to the buoyant force divided by density of the fluid times g, which is 528 newtons. The density of the fluid is 1,000 kilograms per cubic meter and 9.8. The volume that's displaced is 0.54 meters cubed. This is also the volume of the person because that's how much fluid was displaced. So now we know the two key pieces of information that we need to find her density. Her density of the person is equal to the mass of the person over the volume of the person. And both of these things we've actually been able to find. Early on, we found that the person had a mass of 56 kilograms, and we just found that her volume was 0.054 cubic meters. Together, this gives a density of 1,039 kilograms per cubic meter. All right, let's go on to another example. This one's a little bit more involved, but we're ready for it. And I want to do a little bit more than I need to, just to sort of, again, emphasize how we use Archimedes Principle. So we have a 950 kilogram can buoy that's floating vertically in seawater. So the idea is that this buoy basically looks like a cylinder and has a mass of 950 kilograms. The diameter of the buoy is 0.84 meters, And what we want to know is the additional distance the buoy will sink if an 80-kilogram man stands on top of it. But the first thing that I'd like to do is I'd like to help you see how we could figure out how far the buoy is underwater in the first place. Because we expect, if it's a buoy, we don't think that the whole thing should be underwater. Basically, the buoy will only displace as much fluid as it needs to in order to float. So here, again, the diameter is 0.84 meters, and the weight is mg, and then we also have a buoyant force. So the buoyant force minus mg is equal to 0. The buoyant force is equal to 950 kilograms times 9.8. But this is also equal to the weight of the displaced fluid, which means this is the density of the fluid, the volume that's displaced, and G. Notice G's on both sides. I'm going to get rid of it. So I'm going to find the volume that's displaced is going to be 950 kilograms divided by rho. This is seawater, and so we look up in our book and find that seawater has a density of 1,030 kilograms per cubic meter. Remember, seawater's a little denser, that's why you float easier in the ocean. I find that this gives me a volume of 0.9223 cubic meters. Now, what I'd really like to figure out is what is H? What is the height, which represents how much of that cylinder is underwater? So the volume that's displaced is equal to pi r squared times h. And now I can find h is equal to the 0.9223 cubic meters divided by pi r squared, which is going to be 0.42 squared. Be careful, you are given the diameter, not the radius. And this turns out to be 1.66 meters. And so that's just an example. This isn't actually answering the question, but what I wanted to do is I wanted to show, how would I actually figure out how much of the buoy is underwater? Now we're going to go and answer the question about how much further will it have to go down. Let's think about that. So now I have the buoy, and now I got this guy standing on it. And so I have the mass of the buoy times gravity, but I also have the mass of the man times gravity, and then I have the buoyant force. So it should stand to reason, hopefully you understand that this H prime is greater than the H that we just found, because when you put the additional person on top of the buoy's going to have to sink, and what will happen is then it will displace more fluid, and then that amount of fluid is going to offset his additional weight. Here we have the force, buoyant force minus the mass of the buoy times gravity minus the mass of the man times gravity is equal to 0. So basically, though, what I am realizing here is this buoyant force is offsetting the weight of the buoy and the weight of the man. So I actually could just sort of stick with the weight of the man and think about what buoyant force would be responsible for just offsetting his weight. So let's say the force of the buoyant force for the man has to be equal to the mass of the man times gravity. And this will be equal to the density of the water times the volume displaced because of the man times gravity. This will just make it a little more shorthand, figuring out what the volume is that's displaced simply because of the man. And then if we do that, the height that we will find will be the additional height. So I'm going to get rid of gravity here, find the volume that's displaced because of the man is going to be equal to the mass of the man times the density of the water. So it's 80 over 1030. Density of seawater is 0.0777 meters cubed, sorry. And so then I want to find the height. So the volume displaced because of the man we found was 0.0777 cubic meters, which is equal to pi r squared h man. So what I'm trying to figure out is, in a way, what I've done is this total h prime is due to h due to buoy, and then an additional h due to man. And that's the total height. But I've made it a little bit easier so I only have to, I can find that height of the man just directly. So the height of the buoy that's submerged due to the man, which will be the additional height, is going to point 0.0777 pi 0.42 squared, which is 0.14 meters. So the additional distance that the buoy will sink is going to be 14 centimeters. It should make sense that it's significantly less than what we found for the buoy, simply because the man has a significantly smaller mass than the buoy does. Hopefully these two problems have given you a little bit of a better idea of how we can use Archimedes' principle to solve problems.